Unit 2 work and energy. Now we can look some more portions. Energy diagrams. And energy diagrams of a harmonic oscillator, energy diagram of inverse square force, and energy diagram in the case of interaction between two atoms. Energy diagram is nothing but a diagram in which the total energy E or the potential energy U are plotted as functions of position. From the energy diagram we can gather useful and interesting information regarding motion, whether it is bounded motion or unbounded, whether it is in equilibrium. All these things can be understood from the energy diagram. First we consider the case of a harmonic oscillator. The energy diagram for the one-dimensional harmonic oscillator is given below. U E, that is the total energy E, and the potential energy U is along the y-axis and position along the x-axis. U is plotted like this. This straight line is the total energy E. This parabola corresponds to the kinetic energy. Kinetic energy K is equal to E minus U. The system is conservative, hence the total energy is constant. That is, K plus U is a constant E, or K is equal to E minus U. Kinetic energy is equal to total energy minus potential energy. The total energy is represented by the horizontal line. And since the kinetic energy, that is half mv square, cannot be negative, square of velocity, that is, it cannot be negative. The above equation says that half mv square is not negative, that is E minus U is positive definitely. K cannot be negative means K is positive, that is E minus U is positive. E minus U greater than or equal to 0, or U can be taken this side, E greater than or equal to U. That is, fixing the total energy puts the limits to potential energy. Total energy will always be equal or greater than potential energy. The potential energy is such that the system can go up to positions x1 and x2. Potential energy is fixed. It can go up to x1 or x2 on either side of the 0. In other words, motion is restricted between x1 and x2. The motion is restricted between these harmonic oscillator. Motion is restricted between these 2 points, x1 and x2. So these points x1 and x2 are called turning points of the motion. x1 and x2 are called the turning points of motion. The diagram says that kinetic energy is maximum when potential energy is minimum. K is equal to E minus U. K is maximum when U is minimum. Here K is maximum, but U is 0. This happens at the equilibrium position x0. This point is called x0. K max equal to E. Maximum kinetic energy means maximum speed. Half mv square is the expression for kinetic energy. That is, when kinetic energy is maximum, speed will be maximum. That is, the particle crosses the equilibrium position with maximum speed. When it crosses this point, this is the equilibrium point. Here the kinetic energy is maximum, that is, velocity is maximum. The particle crosses the equilibrium position with maximum speed. And as the particle crosses the equilibrium position in either direction, it is slowed down by the spring. It is slowed down by the spring and comes to a momentarily rest at turning points x1 and x2. These are the 2 turning points. At these positions, particle experiences restoring force towards the origin. At x2, force towards the origin. At x1 also, force is towards the origin. The particle then moves towards the equilibrium position with the increasing kinetic energy. Here its kinetic energy becomes low, and at this point it is forced towards the equilibrium point and it increases the kinetic energy. And this process continues by executing simple harmonic motion. When E increases, the turning points move away from the equilibrium, but the particle cannot move away freely. If the total energy E is decreased, the distance between x1 and x2 decreases, implying amplitude of oscillation decreases. This is the amplitude of oscillations. If the total energy is decreased, this total energy decreased, it becomes to the downward, then the amplitude decreases. If E is further lowered, straight line, this becomes here, and amplitude is further decreased. When E is equal to 0, U is equal to 0 and K is equal to 0, this is the 0 position. The particle is at rest at the equilibrium position. The above discussion shows that the motion is always bounded. That is, in the case of a harmonic oscillator, the motion is always bounded. Now let's look at the energy diagram of inverse square force. Potential energy of inverse square force. Inverse square force is nothing but F is equal to Kr by R square term. Kr, unit vector R. R cap is here. K into unit vector R by R square is the inverse square force. And the potential is given by U is equal to K by R. Force is conservative here also. So the total energy is conserved. And when R decreases, the potential energy U, which is K by R, increases. But we cannot decrease R beyond a minimum value at R is equal to R minimum. This is the minimum value where E becomes U and kinetic energy is equal to 0. When E becomes U, E minus U is equal to 0 and kinetic energy is 0 at this point, R minimum. Again decreasing R, U increases. When we are decreasing R, U will increase. Since E is constant, kinetic energy turns out to be negative. If U increases, kinetic energy becomes negative. This is not possible. Kinetic energy cannot be possible because it is half mv square. Hence the particle can go up to a minimum distance called this R minimum. This distance R minimum is called the distance of closest approach, beyond which we cannot decrease the distance between two particles. When R increases, potential energy decreases. U equal to K by R. The potential energy vanishes only at infinity. It will become 0 only at infinity. Thus the motion is unbounded. Energy diagram for the interaction between two atoms. When the one-dimensional harmonic oscillator potential half kx square, we obtained bounded motion where when an unbounded motion is obtained, U is equal to K by R. Now we can look at the case of two atoms. At large separations, the atoms attract each other by the van der Waals forces. Van der Waals force varies as 1 by R raised to 7. As the atoms comes closer, the electron cloud begins to overlap, producing strong forces. When the atoms are brought near, the van der Waals forces disappears and the strong force of attraction between them appears. In this region, force is either attractive or repulsive depending on the details of the electron configuration. If the force is attractive, potential energy decreases with the decreasing R. At a very short distances, the atoms always repel each other strongly so that U increases rapidly as r becomes small. The energy diagram. Now we can look at the energy diagram for a typical attractive two-atom system. This is the energy diagram. When E is greater than 0, E, total energy E, which is greater than 0, it is unbounded system. When E less than 0, it is bounded between these two boundaries, R1 and R2. From the figure, we can conclude for E greater than 0, the motion is unbounded and atoms are free to fly apart. As E is increased, the distance of closest approach, R minimum, does not change appreciably. That is, R minimum is not sensitive to energy of collision. If E is negative, that is, E is less than 0, the motion is bounded for both small and large separations. The turning points. Here turning points are R1 and R2. This says that the atoms can never closer than R1 or move farther apart than R2. It can move in between R1 and R2. This is the bounded condition. Then next is small oscillations in a bound system. For all bound systems, potential energy has a minimum value at the point of stable equilibrium. As a result, the bound system oscillates like a harmonic oscillator if it is slightly disturbed from its equilibrium. About the stable equilibrium point, the curve is almost like a parabola which corresponds to harmonic oscillator. If the total energy of the particle is very low, then the motion will be restricted to the small region where the curve is nearly parabolic.